Hi everyone, Mr. Boltri here, bringing you video 6.5. We're going to talk about equations associated with oscillation motion. So first, we're going to talk about how can you prove that something is in simple harmonic motion. Then we're going to talk about parametric equations and their relation to simple harmonic motion and circular motion. So first, proving something is in simple harmonic motion requires an understanding of the definition of simple harmonic motion. So we've sort of theoretically defined simple harmonic motion as motion that is subjected to a restorative force. And the important thing about that restorative force is it always points back towards the equilibrium position, bringing the object back to that equilibrium position, and it is proportional to the distance away from the equilibrium position. Not all restorative forces are proportional to the distance away, but in order for the object to be in simple harmonic motion, these two conditions must be met. And we can actually show that any object for which both of these conditions are met adheres to this equation. So this is like the equation for simple harmonic motion. Basically, the acceleration is proportional to some restorative force, because Pham law, the acceleration is going to be proportional to the restorative force, where this is the angular frequency squared, and this will allows us to calculate a whole bunch of stuff, and then that is proportional to the displacement. So the acceleration, which is the force pointing back to the equilibrium position. So the force points back to the equilibrium position and is proportional to the distance away from the equilibrium. So this is the theory, and this is the equation behind simple harmonic motion. So what does that look like if you're asked to prove it in a problem? So let's prove it for a vertical spring. We've already proved it for a horizontal spring. Let's prove it for a vertical spring. So for a vertical spring, the equilibrium position is not at zero. The equilibrium position, the point at which it's oscillating around, is at the equilibrium position of the spring. So that is where the net force equals zero. Net force equals zero is the equilibrium position. That's where the force spring equals the force gravity. So at that position, we can say the force spring, which whatever stretch that is, we'll call it y naught, equals mg. So that is the equilibrium position. This is true at the equilibrium position. The forces are equal at the equilibrium position. So if we move it to a position other than the equilibrium position, for example, this extension position, well, then Pham law still holds in effect. We get the force spring minus force gravity equals, now there's going to be an acceleration on that mass. So this is the force spring, and we just showed earlier that the force gravity equals this. It's convenient in this problem because the force gravity is a constant. So we can just substitute in the spring constant times that y naught equilibrium position stretch in for force gravity. So we can factor out a k from both of these and get y minus y naught, divide both sides by the mass, and then substitute the acceleration for the second derivative of the position. And you'll notice that this is basically the equation for simple harmonic motion. We have the second derivative of the position. The acceleration is equal to some constant, which we can say is the angular frequency, times what is this? This is how far it is away from the equilibrium position. Y minus y naught is how far from the equilibrium position. So this allows us to show that the second derivative of the position equals some angular frequency times how far it is away from the position. We can, the equilibrium position, we can say that this motion is simple harmonic motion because it meets those initial criteria. It also just meets the theoretical criteria of the restorative force always points back to the equilibrium position and is always proportional to how far we are from the equilibrium position. Thankful to Hooke's law and how force of springs work. They are dependent on y, how far you are from that equilibrium position. So that is how to prove it for a vertical spring. Let's do one more example just because this comes up pretty frequently in FRQs in terms of how to show something is or is not in simple harmonic motion. So you'll remember this from last semester, way back in FRQ 15 last December. We were given an object that is moving inside a hollow planet. And the first step, it was so important, they gave it to you in the first step. It says basically prove that this is true. F equals negative c times r, where c is 4 pi times the universal gravitational constant times phi, the density of the planet, times mass divided by 3. And we know how to prove this, and you're going to have to remember how to prove this before our test, which covers chapters 6 and 7. But the most important thing is we are given in the problem that the force equals negative c times r. So I'm going to highlight that. And then we were asked, write an equation that could be used to calculate the time it takes for the ball to move from point B to the center of the planet. So from here to here. It's not necessary to solve this equation, but we should be thinking about oscillatory motion. Because if it moves from point P to the center, then it's going to keep going very fast to the other side of the planet and then oscillating back and forth. So what they're basically asking is, what is a fourth of the period? So if we can figure out what the period is, we can figure out what the fourth of the period is. So we have to write the equation basically for simple harmonic motion, because that's going to give us the angular frequency with which we could solve the period. Okay. So let's go back to proving that it's in simple harmonic motion, just so we can go and do the whole angular frequency thing. So the net force we were thankfully given in the problem is negative CR, and we can prove that, equals the mass times the acceleration mass of the little object, negative CR. So then we can divide both sides by A and then replace the acceleration, divide both sides by mass, and then replace the acceleration with the second derivative of the position. And we can show that negative C over M times the displacement, or times how far it is from the center, the equilibrium position, equals the second derivative of the position away from the center. And hopefully by now this is looking familiar to you. This is the equation for simple harmonic motion. So we could use this to say that this object is in simple harmonic motion with an omega, an angular frequency of C over M. Or that would be the omega squared. So omega would be the square root of C over M. And then we could use that to solve for the angular period and then, or angular frequency, and then we could solve for the period, and then we could solve for the time from P to the center of the planet. Now, we're not even asked to solve for all that. All we're asked to do is set up this equation. But if you set up this equation and then say, okay, well, I can use this part to solve the simple harmonic motion equation, and then you are going to get full credit because you are demonstrating a lot of understanding of what's going on with physics, specifically the intersection of planetary physics and harmonic motion. Speaking of the intersection of planetary physics and harmonic motion, let's talk about how we can use parametric functions to represent circular motion. So actually, to do this, let me switch over to Desmos, because that is going to allow us to just play around a little bit more with the functions. So here I have a parametric function. This is the function, and this just represents a dot at a given time. So we have a times the sine of omega t for our x position, and then a times the cosine of omega t for our y position. And you'll notice that when I set an object rotating around that, it moves basically if it follows the path of the circle. And the reason why this makes sense is because if we look just at the x direction, kind of canceling out the y direction, this is something, let me move that up. This is something that is sort of oscillating to the left and to the right, following a particular pattern. And then if we do the same thing, but instead we focus our attention only on the y direction to make the x direction 0, well, what's that's going to look like is, again, an oscillation in the x and y direction following that simple harmonic motion that we've already talked about. So if we look at both the x and the y directions together, what that looks like is a very nice circular oscillation motion. So we can actually use this. This is called parametric equations. We can use an equation that involves sine and cosine. This is the x position and this is the y position to represent an object that is moving in a circle. Which it makes sense because the way that we got the whole cosine thing was by using our analogy to circular motion. So this represents the y component, this represents the x component of an object that is moving in a circle. So a couple important things. In order to say this moving in a circle, we have to say that the amplitudes of the circle is the same. For example, if I were to double the x component, you see how it stretches out in the x direction. But this is fine because this is basically an ellipse. And those are useful when we're talking about interplanetary motion. The same thing, I could double the y position, and then it stretches out in that direction. And again, this is fine. It still like follows all the rules of kind of oscillation motion. It's just not a circle. So the time where things get really weird, though, is where we try to change the omega. It's really important that the omegas stay the same, because let me just show you what happens if we double the omega. So now it's following, it's going through some trajectory, but it is not the kind of trajectory that we were thinking that it would go through. So what I could do, or same thing, if I change the x component, then it just is no longer operating in circular motion. But this actually can get pretty fun. We can do some really weird shapes with this. I don't know, I think that's really cool. It's not really super relevant to our class, but you can model some pretty complicated oscillation motion using this kind of setup. But let's get it back kind of to normal circular motion. Circle is where the amplitudes are the same and the omegas are the same. If the amplitudes are different, it's going to be an ellipse. And if the omegas are different, it's going to be some crazy other motion. So last thing, if we change the A, that just changes the amplitude, the sort of diameter of the radius of the circle that we're working with. And if we change the omega, then that makes it rotate either, let's see, a larger omega means it's rotating faster, and a smaller omega means that it's rotating a lot slower. So that makes sense because we've said that omega is basically the angular frequency, or if we're talking about actual circular motion, it's the angular velocity. So hopefully that all makes sense to you. This is just, I've seen like 2 multiple choice questions involving needing to know kind of this parametric stuff. So I wanted to at least show it to you. We don't need to spend like an abundance of time talking about this. So actually, this is Mr. Boltri wrapping up video 6.5, our last video of AP Physics. I'm looking forward to doing some practice problems with you in our next class, and then moving towards getting ready to end the year. But for now, go Bears.